Hello and welcome to this Intelligent Light webinar. Today we're going to look at how FieldView 17 gives you easy access to bring CFD data into analysis tools. My name is Shane Wagner. I'll be your host and moderator. With me today is Marie Lefebvre, the FieldView Product Chief, and later we'll be joined by Steve McInnim, Customer Applications Engineer here at Intelligent Light. We want to thank everybody for joining us today and call your attention to the chat feature in the lower left corner of your ReadyTalk window. You can use that chat feature to ask questions at any time during this webinar. So with that, I won't delay any further and pass things over to Yves-Marie.
Thank you, Shane. Thank you, and hello, everyone. All right, so let's go on and talk about what we've added to FieldView 17, especially for making it easier to access your data for CFD and CFD data analysis. So I'll start with a statement, which is that data is changing the way people are currently doing their job. Data is everywhere around us, whether it's about when you read about accidents caused by self-driving cars, you use face recognition to unlock your phone, all these things, but it's also now affecting more and more people, not in their daily life, but more importantly in how they work. And if you think about medical doctors, lawyers, and researchers in many fields, they are using more and more solutions like artificial intelligence, data mining, machine learning, to unleash the power of all the data that we have. And we're getting to a point where CFD is being impacted too, and it's only going to be impacted more in the future. So given that at Intelligent Light we consider that our goal is to change the way people do CFD to help them get more information, get more insight from their CFD results, obviously we had to be involved in this topic. So it started for us back in 2012. The first project for us on this topic has been an Air Force SBR contract, during which we've been working on proper orthogonal decomposition for analyzing and compressing results from complex turbo machinery simulations, and you can see a picture over here on this slide. So we've been involved for quite a long time in this topic. We've been having ongoing projects, and the most recent one I want to mention is when our founder and general manager, Steve Legansky, has been invited to present at the first joint US-Japan workshop on data science and CFD, a great event that happened in March in Tokyo, putting together mathematicians, experts in model analysis, and CFD researchers and practitioners, and trying to get them together to extract as much as possible from these new methods for specifically CFD usage. So why is that interesting for CFD practitioners? What are the benefits of model analysis in general? You can see a few applications here on this slide, but basically it comes down to what you can do with this approach. Register the models allow you to build, well, as the name says, reduced models. And so if you have complex flows, if you have very long unsteady simulations, you can obtain something that is smaller, that is lighter to use, a model, and you can use that for further simulations or further computations. Register the models can also be used for compression if you have a large number of unsteady results, and it goes back to that SBR project that I mentioned in the first slide. And eventually, ROA, so reduced order analysis, is really about using the same modes obtained from model analysis, but this time to gain more understanding about the physics of your complex flow field. Now, what you may already see from the various jargon that I'm using, or if you're familiar with the matter, there's a very large number of model analysis techniques that can be used, spanning from Fourier transforms, singular value decomposition, proper orthogonal decomposition, dynamic mode decomposition, just to name a few, and each one of them comes in different variants. Each one has a preferred field of application, drawbacks and advantages. So it's really hard at this stage to find out which methods should be applied in general to any CFD simulation. So the result for us was that we had to come up with a solution that will allow people to experiment with these methods, starting from FieldView, and also have the ability to plug in any work that they could already have done. So we needed to put together kind of an open framework based on FieldView, which again will let users plug in their own model analysis techniques, or also build on examples that we are providing at Intelligent Light, either for consulting or from some of the examples that we provide with the FieldView 17 installation package. So the next slide is going to be a very simplified view of this framework. What we've done is to provide ways out and back into FieldView. We've provided a new math file export. Surfaces can be exported to this format, which is great. It loads very easily in MATLAB or any of its open source equivalents. And the same can be done with a CSV export, which, as you know, opens really well in Excel. But you can also find a lot of libraries, especially on Python, that will parse CSV files very easily and will let you then do additional mathematics on that CSV export. So that's for the way out. And then we're providing a way in as well. Especially you can query a data set based on a subset of points that you will have defined either in MATLAB, Excel, or any other program, and written back to the math file format again, or the CSV format again. So it seems simple like this. Really, what we are trying to do here again is an open framework to let you more easily get data in and out of FieldView and do more analysis after that. So to give you some ideas of what could be achieved with this method, we're going to go through a two-steps demonstration. So let's look at what we'll do in part one. So in this first demonstration, we'll work with an unsteady data set. We'll export the surface to CSV. We'll show you that both for one time step and then for several time steps for the unsteady simulation. And we'll use a Python script to compute an FFT of the pressure coefficient for a few significant points. And we'll plot that then on the plot that you'll see on the screen here. So with no further delay, let's go to demonstration, which will be more exciting for you people. And let's bring up FieldView that I have over here with data preloaded. So this is a data set that we are going to work with. You can see that if I animate it quickly, it's a simple rectangular cylinder. So everyone is familiar with what will be happening with such a flow. We have a classic problem of vortex shedding. We have von Karman alternated vortices that we see being carried over here in the wake. So something very standard, but I wanted something that will where everyone will be comfortable with the physics, so then we can look at the model analysis methods and not get that in the way. All right, so let me stop this animation. So we have our data set over here. What I'm going to do is create a second coordinate surface. I'll create it in the mesh display type. All right, and what I'm going to do next is I do not want to export this entire mesh. Although even if it's 2D, that's a pretty large cut, and we are not going to want to do model analysis on all these nodes. There are several reasons to that. For instance, if you're going to do SVD, you will want to minimize the size of the matrix you're working with and really only focus on an area of interest. Here, as we are going to do FFT, we are going to do it for a small number of points, so there's no reason to export hundreds of thousands of points in that export. So let me scale that down. All right, we'll go from .3 here to say .7. I'll do the same for Z as well. All right, like this. So you can see here, if I zoom in, this rectangle is a surface that we'll be working with. So the first thing I want to do is export this surface to the new CSV format. So I'll go to Tools, Export As, and in this panel we've provided these two additional options, Mat File and CSV. I'll go for that. We'll call it just Webinar Test. Okay, let's go to this directory where we have just created the CSV file. If I double-click on it, it will open in Excel. So you will see that it's a nicely formatted file. We've got columns with X, Y, Z, and a number of scalars that were current in my dataset. But what I like to use more is an editor, a text editor to look at CSV. That gives you another idea of the formatting here. You can see that we also have a header that is useful. It gives me the time step, the physical time of the solution, and another way to look at all the columns that we have exported. So we have, again, X, Y, Z, and all the current variables that I had at that stage in my session for this particular surface. So that's how you do it for one surface, one time step. Next, let's try to do that for a number of time steps for this unsteady simulation if I want to do model analysis over time. So we go to Tools. Now we'll do a transient export. And from that point, you can see that I can select the beginning of my sweep. I want to scope that down so that we don't have to wait for too many time steps to be exported. And I will hit Export As. Put it in the same directory. All right. Let's call it Webinar Test 2, and I will launch the export. So this is also, a point where making the surface export smaller is going to save you time, and you want to have smaller files. Going back to this directory, you can see all the CSV files that have been created automatically with a time step increment. So that's quite easy, and it's just really the same file that we get. All right, so it's kind of a cooking show we are doing here. Didn't want to do the export in front of you for 900 time steps, but we do have that over here. I've pre-created those 900 CSV files for all my tab steps, and so the analysis will be based on all the time steps that I have available. I'll move on to a Python terminal here, and so we'll use a prepared Python script that I've called example FFT. I'll launch it and then explain what it's doing. All right, so you can see first that it found my 900 time steps. And what it's been doing is using different Python libraries. So we use NumPy for linear algebra. We use matplotlib for plotting. And by the way, all these open source libraries are provided with FieldView 17 now. So if your company won't let you download and install these open source components, here they are, right in FieldView 17. The script itself is from Intelligent Light. We can provide that one. Let us know if you're interested. And there are also more that are provided in the installation. I'll get back to that around the end of our demonstration. So let's go to that FFT plot. What did we get over here? So it's a pretty standard plot. I'm guessing that most people on the call are familiar with that kind of things. We are looking at the magnitude of coefficient of pressure variations in the frequency domain. I just want to mention that this one has been computed after the time average has been subtracted. So that's why we're going down to 0 here for the first frequency bin. The first spike here corresponds to the vortex shedding, really. Again, it's a very simple flow, so there's one frequency for the vortex shedding, and that will also give us the Strual number for that characterize this flow. On a more complex flow, you will get more spikes, obviously. You will see frequencies, for instance, present in different areas of the region, like the turbulent Bourley layers will typically be very frequency rich. And what this plot provides as a benefit is that thanks to the magnitude, you can really discriminate which are the most significant frequencies for the flow you're working with. Didn't mention it here, but each line is for 1 point on which we've followed the CP variation over time. So you could add more points to the script, and the location also was hard-coded, but it will be easy to change that or do it for any location that you're interested in. All right, so that concludes the first step of our demonstration. So let me go back to our slides to explain what we'll be doing next. All right, so in the second part of this demonstration, we will work with the same entity dataset. We'll perform a Cartesian resampling using the new point query capability. I'll explain why we want to do a Cartesian resampling. We will export the output this time using the mat file. I want to show you the other format. And in Octave, we'll perform a singular value decomposition, plot the significant modes. That's what you see in this plot on the right here. We'll create a reduced order representation of the entity flow field and pull that back into FieldView and discuss what we are looking at. All right, so let me share my desktop again. So we are going back into FieldView, and we'll just load another restart file. So we are looking at the same data set, but a different scalar. We want to work on velocity now. So what we have here is a typical O mesh around the rectangle. And you can see that, of course, we have variations in the size of the faces. So this is a potential problem when you do an SVD analysis. If you want to do it based on this computation mesh, you will have to use some weighting factors to account for the surface area of each one of your faces. Or another approach, and that's the one we're going to use here, is to have a Cartesian mesh, the one in black here, that we've imported for you to see, and this is the one that we're going to use for resampling. So this Cartesian mesh has been created in MATLAB. The points locations have been saved into a mat file, and so we'll use a mat file to query our dataset and write the velocity components into a mat file that we'll be able to process in Octave after that. So for that, let's make sure that first I'm on the right dataset. Okay. Then I go to Tools, Point Query. So you can see that all these new capabilities have really been grouped in a new section in the Tools menu. I'm going to Point Query. All right, let me move to the right directory. And it is the mat file that I'm going to pick, which is again storing the location of all the nodes that we are looking at in black here. Next, I need to provide a name for that export. Oops, that will be too far. All right, I'll put it over here. All right, let's call it webinar test again. Okay, and all right, so the file has been created over here. So what we'll do next is open Octave, which again is provided with this FieldView 17 installation. And from Octave, I can see the same mat file over here. So I just have to double-click on it, and it gets automatically imported into Octave, which means that all the variables contained in it are now active. So if we look at what we have available, we can see, for instance, that we have the X, Y, Z locations. So if I'm going to print the first 10 positions in X, you can see that, yeah, we do have a Cartesian resampling happening with regular delta X. And the same can be done if I want to look at my first variable, which is then called S for scalar. All right, I'm getting the first 10 values of that scalar. So what we added in the mat file is also the ability to connect back to your data set. And we've provided what we call the table of contents. So if I do tuck to print the value of that table, the values in that table, so you can see that all the coded names have been stored, but all those names, they are available inside of FieldView. So that really tells me that here The first item is S, and its name is velocity magnitude. So that's the one on which I want to do my analysis. Okay? All right, so let's clear that. I will just quickly reset my environment here to be able to rerun my FieldView analysis. All right, and from that point, I will launch a script. So again, I don't want to go into the details of how it's been coded, but if you're interested, it's all scripts that we can provide to you from Intelligent Light. And what this next step is doing is that it's going now through 900 MAD files that we've exported initially. And we're going to compute the singular value decomposition. And at the end of the process, Octave is going to give us a plot with the most significant modes being visible on the plot. All right, so it will take just a few more seconds. Okay, here is the plot. Let me make that a bit bigger. All right, so what are we looking at? So again, 900 modes have been computed, but then they've been sorted by significance, and you can see the first one over here. So you can see that the line is really dropping quickly, and if we were to do the math from mode 5 and above, really all these modes after mode 5 are contributing for less than 5% of the velocity. So it tells us that the 4 first modes are capturing most of the flow features, and especially the first 2 really are the most significant. So that's a really interesting way to look at the results, and for real case, again, typically more modes will be important, but what you will want to do next is identify what each one of these modes represent physically in your flow field. All right, now that we've done the SVD, based on it I can call another script that we have here. And this one is going to reconstruct data based on the modes. So the idea here is to create, we'll just do it for 20 time steps, again, to not take too much time, but we could reconstruct the 900 time steps. And they will be reconstructed based on the modes that have been computed. All right, so let's go to our demo directory. So you can see here the time steps that have been recomputed. You can check that the timestamp is accurate. So we've just made them, and again, we're using the same cooking show trick, but we have recreated 900 time steps using the same approach, but running the reconstruction in Octave ahead of time. All right, so these files, when I say reconstructions, what we've done is we already had the mesh, remember, from the resampling we've been doing. So we've been using the plot3D function file format to write the reconstructed fields for velocity. So now that we have that in the plot3D format, we can load it back into FieldView. So let's go back to FieldView. I've created a restart to quickly load back all these data sets. So I'll jump to that. You don't have to worry about me loading the data. All right, so what do we see over here? The bottom half is the original data set. You can see the entire flow field. The upper half is the one on which we've done the resampling, if I show you the mesh here. So it's the reconstructed one. The variable we are looking at on the top is velocity magnitude reconstructed from modes 1 to infinity. So that's 900 in this case. And so you can see that we have a really perfect match with the original case. If I go ahead and change the variable, we've exported 3 variables actually. The second one is the same, velocity magnitude, but reconstructed from modes 1 to 4. All right, you can see right away that the shape is changing a little bit, so it's a less accurate reconstruction of our flow field. If I keep going like this and show you the reconstructed flow field for modes 1 and 2 only, it starts to be really interesting. All right, so let's move on to later in the data set, and we're going to launch the sweep. All right, just need to make sure that they are synchronized. All right. So note that I've used merge times. The two data sets are going to be synchronized over time. I will relaunch the sweep. All right, so you can see them advancing side by side. And as we get to that point, that reconstructed field with just the two modes is really showing us kind of too big a vortex. So what is good is that the vortex really has been captured with these two modes, but it's a bit too wide, and especially we're missing some information of what is happening between this vortex and the rest of the flow. So what it tells us really is that modes 1 and 2 account for this main vortex shading that is happening. Now if we add back mode 1 and 4 to 4, you can see that we have a more accurate representation here, so it starts to account for what's happening between the two. So mode 3 and 4 really are a better representation and better take into account what's happening between vortices. And if we go back again to all the modes used for the construction, we see a good match again. So again, what I'm trying to show you here is how modes from the SVD analysis can be used to re-analyze a complex flow field and do reduced order analysis on it. One more word while I'm inside of FieldView 17. From the tools menu here, maybe you've seen that we have another new entry. If I go on and click on FieldView 17 Analysis Demo, so this new panel is giving you access to more options. You have the ability to run time history plots, FFT analysis, or POD. The two first you can run both on a demo or your own data. POD can be done on a demo, or you can also start Octave. And so here, if I want to do an FFT analysis on my own data, I will get access to a new panel that will let me define the points location when I want to do the FFT and the variables based on which I want to do it. So we're also providing an interface for it, but it's all based on the same components in the background. So again, NumPy and Matplotlib and other Python libraries that are provided. And the scripts for that we're calling in the background are also provided to you as a source. So you can use them as examples, or you can contact us if you're interested into more scripts. All right, so with that, let me close this panel and go back to our slides. Okay, so we're done with the demonstration here, and just want to explain again that a big part of the thing we've been trying to do in FieldView 17 is to provide this data analysis framework, which is really open, letting people to plug in any method that they have or build more based on our expertise and the scripts that we can provide. So you can export from FieldView to Matfile and CSV, starting with coordinate surfaces and unstructured boundary surfaces. We'll be adding support for more objects in coming versions of FieldView, but these are the ones that really stand out at the highest priority. You can do high-performance point query, where the stage now, where in FieldView you can resample your data on any sample, and using point query, the speed will be in the range of hundreds of thousands of probes per second, which is really high. And again, this distribution includes analysis examples and all the tools like Octave, NumPy, and Matplotlib, which are part of our distribution. But of course, there's a lot more to FieldView 17 that we won't have the time to cover in this presentation. We've added support for Asian fonts, so that was a very big thing for all our customers in Japan. We've made FieldView faster in a number of areas. Just to name a few, we have a faster built-in Q-criterion variable, which is 11 times faster to create big isosurfaces of Q-criterion compared to the previous version of FieldView. We have a much faster hard poly reader, a 40% faster XDB read, and which also affects all the surface-only readers. And we've made significant advances in the area of in situ, with a number of solvers now being able to export directly to or extract XDB format straight from the solver without even going through FieldView. So if you're interested into more of these new capabilities, full details can be obtained from our interface. If you go to the Help menu, you have a direct access to our PDF, Welcome to FieldView 17. And then there's also the What's New in FieldView 17 document that can be obtained from our website. I've put the URL in the bottom right corner of this slide. Just a quick note to say that this is our last release to support 32-bit Linux. Will be dropped for the next version of FieldView, and it was already the case for 32-bit Windows. FieldView 16.01 was the last release for that. All right, with that, I'm done with my part, I believe, Shane.
Well, thank you, Yves-Marie. I hope that everybody has enjoyed the demonstration and the information provided here. And we'd like to ask that if you feel that getting your CFD data analysis CFD data into analysis tools faster and easier is valuable to you, then contact us. We're ready to work with you. We have on-site training available. We can do short mini trainings via the web. We're also working on a new tutorial that's coming soon. We'll let you all know about that. And of course, we have our custom engineered solutions team, which is working in the areas of advanced workflows, automated report generation, and we have some people on staff who can incorporate this type of data analysis into any of those workflows. So again, we encourage you to contact us, reach out to your to your support representatives here at Intelligent Light or your sales representative. We're happy to help. We're going to move on to the Q&A session now. And with me, of course, is Yves-Marie, and we're also welcoming Dr. Steve Makinen. Say hello, Steve.
Hello, everyone.
Okay, great. And so I'd like to point to the chat window there. The lower left corner of your ReadyTalk session is a chat window where you can ask questions. I will ask them on your behalf, and we'll get an answer from Steve or Yves-Marie. And so we'll begin. We have a question. Do you distribute example scripts, Python or MATLAB, to facilitate writing Plot3D files to bring results of data analysis back into FieldView?
Yeah, I'll take that one. By distribution, we don't distribute them yet in the FieldView installation directory. But we do have them, and we'll be happy to share what have demonstrated today, which included the ability to write back the results to Plot3D. So the answer is yes, and if you're interested, you can contact us, and in the case of that particular user, we'll follow up with them to provide the scripts.
Good, right. So the person who asked that question...
He said Python or MATLAB, so I guess he's looking for both, or, well, I guess he'll let us know whether he's more interested.
We will follow up with that person, yeah. Okay, good. Here's another one. We showed cases where the whole solution has been saved at every time step. What are my options if I am dealing with very large cases other than in situ instrumentation?
Okay, so well, the case that we were working with here was 2D. So yeah, the full data set was saved for all time steps. The same analysis could totally be performed if we had just the same cut plane for full 3D case, right? So a lot of solvers have the ability to make a cut and write that over time. So that can either be an export of the solver, and then you work with a much more reduced extract of the large steady simulation. For other solvers, in situ is required for making that export. I'm talking about knowing which solver we are talking about here. Mm-hmm. But again, a lot of solvers have the ability to already make some extracts for generating the kind of data that you need for performing such analysis.
Yes, if that person has a specific solver they're willing to share with us, we might be able to comment further on how to export a slice. OpenFoam, he says.
All right. So yeah, I think Steve could maybe help me and complement if he has additional insight on this question.
Yeah.
Yeah, actually, one thing I wanted to at least clarify, maybe it might have been a misunderstanding. The CFD solution was the entire CFD domain was, saved, but the extracts were only a subset of that. That's a capability that FieldView is very good at. So you can really just use FieldView sort of as a data management tool. So you just extract just the subset of information that you want to work with in the rest of your data analysis. And also it's possible to use FieldView, for example, as a pre-processing, and then you can create XDBs. And then from the XDBs, then you could even just take a subset of those for the data analysis, subset of information from the XDBs. And if you're not familiar with XDBs, those are just extracts from the entire flow solution at whatever regions that you're interested in. Hopefully that answers the questions.
Yep. Yeah. That's a good point, Steve. What I would like to add, since the participant has added that is using OpenFOAM. So OpenFOAM has the ability, correct me if I'm wrong, but I think it has the ability to export cut planes. So they will put you straight in the same points that we were showing in that demonstration. The analysis could then be performed on the cut planes. If you were to save the full results over time, you could also, some customers do that, run FieldView in batch. Each time a time step is saved, you could also process that, generate the extract in batch, and work from the extract. So there are several options before a full in situ instrumentations that are possible. And I'm sure I mentioned it, but the export from OpenFOAM will typically be in VTK format, and of course there's a VTK reader in FieldView.
Okay, good. All right, so again, I encourage people to use the chat feature if they have more questions. We'll be on for a few more minutes. Another question is about the value of modal analysis, and what is the value beyond just another way to visualize your results?
All right, I'd like Steve then to answer that one.
So I think the modal analysis is used in many other areas of structural dynamics and control theory for planes and cars, so forth. And so this essentially now allows this methodology to be used in analysis of fluid dynamics as well. I think a key thing to keep in mind about this approach is that modes allow the engineer to relate the attributes of a product to the modes, and then the modes can also be related to the dynamic response of the system. And so from that, then you can use the modes essentially as a means for mapping between attributes and response, and then you can figure out how to improve the design going forward as you go through your design iterations. And that's something that we've actually do have experience with and have done that.
Good, thank you. I don't see any more questions coming in. We will wait for a few more minutes to see if there are a few more questions. Eve Marie and Steve and I will be on the line. But as this is the end of the presentation that we have, and there are no more questions coming in, I'd like to thank everyone for participating today, and again encourage you to contact us to find out what's possible. Perhaps we've just started a seed in your mind about what's possible. Let's talk about it. Bring us in to the conversation or to the thoughts that you're having, and we're happy to explore that with you. Thanks again for everyone for coming. And again, use the chat feature. We will be on the line for another few minutes answering questions. Marie or Steve, did you have anything else you wanted to add? Any thoughts you've had?
One thing this is Steve Mackinnon. One thing I thought to add about the first question, which was asking if we have example scripts for writing plot3D files. So as Eve Marie explained before, we do have example scripts for that, and we also have example scripts for writing FEUNS files, and that's unstructured file format. So if you want to extract geometry that's not doesn't lend itself to structured CFD files, then you can also just use FEUNS files.
Good, thanks. Okay, well, we haven't had any other questions. So with that, I think we will say goodbye. And once again, thanks everyone for joining us today.
All right. Thank you, everyone. Goodbye.
Bye-bye.